So welcome everybody. Today is going to be more NP-complete problems. And then once we're done with saying why these problems are all hard, we have to solve them anyway, and so next time we'll be coping with them. So how do we get approximate answers, or how do we try to do better than exponential time most of the time? So, but today we're just going to show you more problems that are NP hard, NP complete. And so let's just remember the definitions. So a relation R is all pairs of bit strings X and W, where X is an instance of a problem. So it's the input, and W is a witness for a solution. That is, a proof that the problem is actually solvable. And so, in one example was this is a network with a source and a sink, and this is the max flow. So given that, we define our complexity classes. And P was a polynomial time one. So this is the complexity class of problems, of relations, where if you want to decide for that particular relation whether X is solvable or not, and that is going to be 1 if X solvable, else 0, that costs polynomial time in the size of the input, which I use absolute value sign to indicate. So that was P. And then we got to define NP, which was all relations R where we can check a proposed witness in polynomial time. So the canonical example that we started with last time was circuit satisfiability. And so X is a circuit. Question? And W are the inputs. And you just evaluate, and what is the algorithm to check it? You just evaluate the circuit where you plug in those inputs and see if you get a 1 or a 0. So that was the simple example. And then we got to define the class of NP, which is, or NP hard, I should say. So a problem A is NP hard if you can reduce every problem to solving A for all B and NP. In other words, if you have a subroutine that magically solves A, you can use that to solve every other problem in polynomial time. And what we're assuming here is to do that is, of course, we have to convert the input of B to the input of A, so you can run the subroutine for A. And we have to take the output of A and convert that to the output of B, and those both have to cost polynomial time in the input of A. Okay, so that's what it means to be NP hard. And finally, the class of problems that's going to occupy us mostly today are NP complete. So A is NP complete if it's NP hard, so you can use it as a subroutine to solve anything, and it's NP. And the canonical example we did last time was CSAT. This is just sort of a review of the definitions. Are there any questions about that before I sort of sketch the tree of how we're going to prove it? So I'll remind you what we did last time, and then I'll tell you what we're going to do this time. So the first problem that we showed was NP-complete, was circuit satisfiability. You can reduce any problem to satisfying a circuit. And then we reduced that to satisfying a Boolean expression in conjunctive normal form. So something that looks like this. Then we reduced that, this is all just a review of last time, to 3SAT, where you're allowed to have at most 3 variables in any of those clauses. So we did that last time. And then what we did from there was independent set. So in that case, it's given a graph. Let me draw a really simple one. Find the subset of vertices that aren't connected to one another, so no edges connecting them, that's as large as possible. So for this particular example, I could choose that vertex, and that vertex. None of them are connected, so they're independent, and I can't pick more than 3. So that's the independent set problem. That's the answer to the independent set problem for that really simple graph. And from independent set, I did vertex cover. And let me just show you the answer for that same little graph. And so now what I want to do is find the fewest vertices that touch every edge. So that would be that one and that one, because every edge touches one of those. And this is the complement of that. That's how that reduction worked. These are sort of, asking the same question in different ways. And then we did one more, which is finding the biggest clique. Okay. So that's what we did last time. And so now I'm going to finally get to an outline of what we're going to do today. And maybe I'll use one more board for that. So we will start with 3SAT as before, and then we're going to do a problem called 3D matching. And I'm not going to try to explain that in one word here, in a few words, but that'll be the first one I describe. So that's another kind of combinatorial problem. And from there, we'll do something called 0-1 equations. This is just solving systems of linear equations, but every variable has to be either 0 or 1. And so we're going to restrict it to ask, is there a solution where all the variables are 0 or 1? So all the entries of the matrix are 0 or 1, and all the vector entries are 0 or 1. So that will in turn let us do integer linear programming. Or ILP. So it's the standard form of linear programming, except I'm going to add the constraint that the answer has to be an integer. And that's going to turn out to be NP-complete. And from here, should have given myself some more space. So the next one we're going to do, let me go up here, is something called Rudrata Hamiltonian cycle. Or RHC. So that is, you're given a graph, and you want to know, is there a cycle that touches every vertex and comes back to the starting point? And that will finally turn into the traveling salesperson problem. Or TSP, which is, again, find a cycle that visits every vertex once and find the shortest one. Okay, so that's going to be the traveling salesperson problem. And so this is going to be the goal for today, to do, go from here to here and then fill in the rest of that. So any questions? Okay. So let's start with 3D matching. And I brought 4 different colors of chalk because, yes, it's a little complicated. So this will make it easier to understand, I hope. So here's the definition of 3D matching. So I'm given some sets, and of some just objects here, and they all have the same number, k plus 1. And I also have triples. So I have a set of, one of these, one of these, one of these. So it could be, for example, D3, C2, B7, and then another one, D1, C3, B2. Just some finite list. And what I want to know is, can I find a subset of these that match all of these, where each one of these appears exactly once? So is there a subset of triples where each of those sets, entries of the set, so each DI, CI, and BI appear exactly once? Okay, so that is kind of the, so this is motivated as sort of being an intermediate step to get from 3SAT to all these other more practical problems. But this is sort of the combinatorial problem that we want to solve. So I'll move my colored chalk back over here. So we're going to use sort of the same trick that we did before. We're going to build gadgets that out of particular sets of triples that are going to model 3SAT problem. So I need to build something that models a variable, the variable x, and whether it's true or false, by sort of putting together a combination of D's and B's and C's and triples. And then I also need to build a gadget that models each clause. So that's what the trick is. From triples to model variables and whether it's true or false, and clauses. And the clause might be something like X or not Y or Z, because I'm just going to do 3SAT. And so let me tell you what the gadget is for variables. So the motivation is if I have a variable that can only be true or false, I want my gadget to only be a matching in 2 possible ways. And one way will correspond to true, and one way will correspond to false. Okay. For each variable x, this is what I'm going to build. I'm going to use 4 triples. And so now I'm going to start using all these different colors. So the white triple will be C0, D0, and B1. But I'm also going to have a green triple, a blue triple, and a red triple. I hope that's all visible to everybody. So this is what the gadget is going to look like. So that's going to be there. And it's going to be, and I'm going to label these endpoints with the variables it corresponds to. So this will be a D, a B, a C. And then I'm going to have a few more connected this way. So there's my green triple. Here's my blue triple. And finally, here is my red triple. Okay. And so how am I going to, and so before I start labeling it, let's just point out that there are only 2 ways I can do a matching here. If I pick that triangle and that triangle, that triple and that triple, then all of these get matched, and this will have to get matched to something else. Or I could pick the green and the red, and then these will all get matched, and then these would have to get matched to something else. So there's only 2 legal states here where I can match all those. Either I pick the top and the bottom, or the left and the right. And so let me just label them all now. And so here is going to be the idea. If I pick these 2 triples, the red one and the green one, that is going to imply that x equals true. Okay, so that's one possibility. Or I could pick the top one and the bottom one, the white one and the blue one. And that's going to correspond to x equals false. Okay, so I'm going to build one of those contraptions for every variable. Okay. So put another little circle down there. Should have told you all to bring colored pencils today. Sorry. Okay. So that's the gadget for each variable. So how do I build a gadget for each clause? And I'll just do an example of 1, and this is 3 sat, so I only have 3 variables appearing in it. So for this particular clause, and let me just call it clause C, so it has a name, I'm going to add a new entry to the D, to the set of Ds, and a new C to the set of Cs. So I'm going to add one more item to this set and one more item to that set, and I'm going to label it by which clause they belong to. And so how do I make this true? I could pick x to be true. And so how do I make x true? I want to somehow force myself to choose these 2. And so what I'm going to do then is connect DC and CC to either B1 or B3. So the only way to match DC and CC will be to either pick this one or pick that one, forcing me to pick the red and the green, which makes x true. Okay, so that means for x, I'm going to connect it either to the top or the bottom. And so that x refers to the fact that this is specifically the x1. So b1x is that one and b3x is that one. I just pick one of them. And so that implies we need to choose, as I said, the red and the green to make x equal true. Okay, what do I do now? I have to go on to the next variable. And the only way I can, how do I choose y to make this clause true? I'd be choosing x equals false. So for y, I'm going to add these particular ones. So I'm going to say that I either connect it to this side or that side, which means I would have to pick the white and the blue, which means x equals false. So that means we need either the white one or the blue one. Excuse me, we need to pick both of those, white and blue. Yes. And that's going to imply that y equals false. And same trick for z. Okay. So, am I done? So let's suppose that everybody got connected, and there weren't any missing connections here. Then, if there were a matching, if there were a an answer to this question, then I would have chosen one variable from each clause to be true or false to make that clause true. And this thing would have been connected, would have been chosen correspondingly. But remember, it's a little tricky because I have to make sure everybody gets matched. I can't have any sort of missing matches. So if the variable x only appeared one time, then I would only have it connected to the top or the bottom, and then this one would be an orphan and not get matched with anybody. And so I have to fix that. So I just have to make sure every variable appears exactly twice. In that case, one of the appearances will get connected to the top, and one will get connected to the bottom, so everybody will get matched. So this is just a little bookkeeping at the end. But you get the basic idea. Yes? What do you mean by what is it? So if I can do this, solve this problem, then I will have chosen one variable from each clause and set it either equal to true or false to make the clause true. And if I can do that for every clause, then I've solved 3SAT. Yes?
Can we just pick like white and blue to be true and red and green to be false?
No, this was kind of arbitrary. As long as it's two states. Yeah. Okay. So as I said, I have to make sure that I match both of these and both of those, and that would be okay if every variable appeared exactly twice, because then I'd have this matching. But if I have an arbitrary 3SAT problem, every variable is going to appear some random number of times, and so I need a little trick now to take any 3SAT problem and convert it to another one where every variable appears exactly twice. So that's the little cleanup at the end. Okay. So need to make sure each variable, or each, let's say, x prime appears exactly twice. so the first case is if it appears more than twice. So 3 times, 4 times, however many. Let's suppose it appears k times. So for some number k greater than 2. I'm going to add some new variables and make sure that they're all the same, and so I get the same 3-set problem. Okay, so what I'm going to do is replace each variable x by one of these new variables, x1, x2, dot, 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 xk. So they're all different. But I have to make sure that when I'm done, all of these have the same value. So, because that's what I started with. Make sure all of these xi are equal. And they appear twice. Because once I do this replacement, each of these is a new variable that only appears once, and I want to make sure it appears twice. So here's the trick. So I'm going to add this clause. Okay, so let's suppose that I need to pick x1 equals true in order to satisfy x equal true to satisfy the clause. So that means I'll pick x1 to be true, and so for this to be true, that means x2 has to be true, which means x3 has to be true, dot, 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 which means they all have to be true. Right? So that ensures that if I pick one of them to be true, they all have to be true. And what if I pick one of them to be false? Then let's say x1 is false. That means that xk has to be false so that this is true, which means that xk minus 1 has to be false, dot, 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 all the way through. So they're all going to be the same. And so now, and each one of these variables now appears exactly twice, so my construction works. Yes? So if I want to make sure that I satisfy my 3D matching problem, every one of these items has to appear exactly once. And since the only and these by construction are only connected to these, triples, the green, the white, the blue, and the red triples. And so the only way I can match all of those is by picking either both of these or both of those. I mean, I can't pick these two because then that would be in 2 triples. Yes?
Why do each of the variables have to appear exactly twice?
Because when I'm done, I want to have this one matched to one. Yeah, so I'm going to do this trick up there where I take each variable and match it to one of these. And so I want to make sure that I can match both of them, right? Because B1 has to be in a triple and B3 has to be in a triple. So I need 2 appearances, one to connect to this one and one to connect to that one in case I've chosen red and green. And if I've chosen white and blue, then I need to have 2 connections so I can match B0 and B2. Yes? Sorry, say again? No, that would prove P equals NP, I think. I don't think we can do that. Because network flow is, in P. Yes? So I've chosen a clause, and I've given it a name C, but I would number them or something like that. And so those D sub c's and C sub c's correspond to that precise clause above there. And I'll have, you know, a different DC and a different CC for every clause.
What about the B1x?
So there's exactly one B, you know, or there are 4 B's for every variable. So that's why I wrote B1x, because it's the particular 4 B's that correspond to variable x. Yes?
So like if you want to make sure like each of the variables appears like exactly twice, right?
Yeah, I'm not done yet, so, because if it appears once, I got to fix that too.
Yeah, but then like if it appears like more than twice, then
Yeah,
like that we have to add that like make sure that all the x sides are equal, right?
yes.
That already uses like x2 for example, like that already uses it twice. So like what happens like the rest of the
Well, so x2 appears exactly twice, which is what I wanted.
yeah, what about the original expression? We're replacing everything by x2. Won't that like sort of add to it?
Yeah, but I mean, it's still all polynomially larger. It's not, I mean, I haven't made it ridiculously large. But it's an equivalent 3-sat problem. Actually, this isn't 3-sat yet, you know, but because, well, 3-sat means at most 3. That's all I care about, yes. Yes?
How do you choose the k?
I just look at my original 3-sat problem and count how many times x appears. That's k. Okay, yeah, this is a very technical construction. But it's going to be you know, very useful to do all that stuff. Yeah, so this is you know, a technical trick that will let us get to all these other problems. Okay, so this is what you do if a variable appears, you know, 3 or more times. But what if it only appears once? That's also a possibility. So I got to fix that too. So now, if my variable x or x bar appears once, what do I do? So I need to add a whole bunch more triples to make sure that all the b's can get matched. So the problem here is that there are not enough triples to match all the BIs, because, you know, I need 2, one for the top and one for the bottom, or for the left and for the right. So I'm just going to add a bunch more kind of just helper triples to cover all the orphans, if you like. So if there are m triples missing, I'm just going to add lots more to cover every possibility. So I'm going to just sort of, you know, these aren't, I'm not going to add any clauses. I'm just going to add some, you know, D's and C's, D tildes and C tildes, BK. And I'm going to do that for, you know, m times. So I can use, I'll have m of these that I can match up. And I'm going to do this for all of the b's, for all of those, to match the leftover BKs. Okay, so I'm just going to add lots of triples to catch, you know, whoever's left over. Yeah, so these don't correspond to clauses anymore. Sorry. Okay, and that sort of cleans up everything, you know, if I just have single appearances. Okay. Any questions about this? I think that is the end of this complicated combinatorial description of 3D matching. And so now I can move on to the more interesting problem, 0, 1 equations. Okay, yes? I just constructed it that way. The point was that this is constructed so to get a matching, you either have to choose the red and the green, or you have to choose the white and the blue. You only have, there are only two choices that can possibly match all of the D's and C's in the middle. And so since there are two states, and that's exactly what I want, two states corresponding to true and false, and I can pick those kind of arbitrarily. Yeah. Okay, so how much of this detail do I need to leave up? Okay. So I think that, yes. I think I just need to leave the statement up there. That's all the detail I need. So now, how do I reduce 3D matching to solving 0, 1 equations? So what I'm going to do is build a system of equations that corresponds to any stuff that looks like that. So let me just do it for that really simple one up there, and you would just continue building a bigger and bigger one. So what I want to do now is, so what is the 0, 1 equation that's going to be solved, if it's possible, because the answer may be you can't solve it. A times x equals the vector of all ones. Where each entry of the matrix and each entry of the vector is only allowed to be 0 or 1. So that's the 0, 1 equations problem. Just standard linear algebra, but we're restricting to zeros and ones. So here is going to be the trick. My A for my 3D matching problem is going to have one column per triple, one row for each of these entries of the set, so each DI, CI, and BI. So however many there are, there's a separate row for that. And what are the matrix entries? Aij equals 1 if the label of row I, so DI, CR, BI, is contained in the triple corresponding to the column. So the label of column J. Okay, so I think it'll be easier for me to draw a little picture to see what that means. Now I'll just use that bit up there. So what is A for that one up there? So there's going to be one row for every one of these set members. So D0, D1, C0, C1, and then B0, B1, B2, and B3. So those are going to be the rows of my matrix. And then the columns are going to be the different triples. And again, I will try to use colors for this. Okay, let's fill in a few rows. But it's pretty straightforward. So D0 is in both the red triple and the white triple. So that means that's going to be 1, that's going to be 1, but those are going to be zeros. D1 is in the blue and the green So these are going to be 1s, and those are going to be 0s. C is in white and green. Now I'll just do one more. And C1 is in blue and red, etc. Okay. So that's how I'm going to, so this captures everything about the connectivity of my 3D matching problem. Okay. So, so now let me try to interpret. So I'm going to take a vector of x. This is a vector of 0s and 1s. And so in this case, x1, x2, x3, x4. So this is now I'm multiplying a times x. Is this matrix times that vector. And so that means if this is a 1, I'll pick the white one. If x2 is a 1, I'll pick the green one, green column, and so forth. So what does ax sub I mean? So, and so let me be concrete here. So x sub I equals 1, that means we select that triple. So if x1 is 1, that means I'm going to include the first column when I do this matrix vector multiply. So I'm going to get all of the set members that are in the white triple. And if I pick x2 equals 1, I'll get all the ones in the green triple. Okay. So now what is a, now suppose I do this, a times x, and I look at the jth entry of that vector. I've counted something. So what I've done is I've added, this column, maybe this column, maybe this column, maybe this column. So what I'm doing is I'm counting is the number of selected triples in which, let me get this right here, containing the label of row J. Okay, so in other words, how many, so if I is 3, I'm going to be counting how many triples contain C0. Okay, so let me just do a concrete example here. Woo, dusty. So, in particular, I claim that ax equals the vector of all 1s if and only if each row label appears in exactly one column, which means in one selected triple. And that is the same thing as 3D matching. In other words, if I can solve ax equal the vector of all 1s, that means that everybody appears in exactly one triple. So let's just do this particular example here and ask what is, let's suppose I select all the columns. So I'm going to multiply it by 1, 1, 1, 1. And so I'm going to add up all the columns, and then I'll take the second entry. So I'll add up all the columns, and I'll take this entry, and I'll get 0 plus 1 plus 1 plus 0, and that's going to be equal to 2. And that's because D1 appears in both the green and the blue triple. Okay. And so I haven't solved my 3D matching problem. But if I can solve it so that everybody appears exactly once, then I have solved 3D matching. So if I can solve the 0, 1 equation problem for this, in fact, very special right-hand side, then I can solve 3D matching. So that's the reduction. Any questions about that one? Okay, so we did 0, 1 equations. The next one is integer linear programming, which is just a few lines from this one. And I think I can finally erase this picture. So the next one is reducing solving 0, 1 equations to integer linear programming. So suppose I have my 0, 1 equations problem. So what do I need to do here? So ILP, it turns out that merely finding a feasible point, you don't even have to get to the optimal answer, but just finding a feasible point that satisfies the inequalities is good enough to solve 0, 1 equations. So we need to find a feasible x that satisfies all our inequalities. And so that means x has to satisfy that a times x is less than or equal to b, and x is greater than or equal to 0. That's sort of the standard things we have to solve. So the question is, how do I build the 0, 1 equation problem into these, solving these inequalities? So what I'm going to do is convert ax equals the vector of all ones. So let me just write big 1, that's the vector of all ones, where all of the x sub i's are restricted to be 0, 1 to inequalities. So what I want is that ax is less than or equal to 1, and ax is greater than or equal to 1. That will certainly guarantee that ax equals 1, but the inequality is going in the wrong direction, so I just multiply by minus 1. So that's certainly, so now I just have added these inequalities, and now that's the same as guaranteeing this. And how do I guarantee that x is either 0 or 1? Well, I know it has to be at least 0. And so if I insist that x is less than or equal to 1, that's just adding more inequalities of this sort. That means it's greater than or equal to 0. It's less than or equal to 1. I have two possibilities, 0 and 1, because it's an integer linear program. Yes? Yeah, it's component-wise. Yes. Yeah, so I'm just, this is shorthand for component by component inequality. Okay, so I don't even have to solve the optimization problem for my integer linear program. I just need to decide feasibility, and it solves 0, 1 equations. Okay, yes? So, because I want to find a solution to my 0, 1 equations, so I need each x sub I to be either 0 or 1. And since it's an integer, if I insist it's at least 0 and at most 1, those are my two possibilities. And it's at least 0, and it's at most 1. Yes? Because this is the integer linear programming problem, which is, as we just see, NP-hard, as opposed to the regular linear programming problem, which we can solve much more cheaply in polynomial time. right? So it's this adding the constraint that I need an integer solution is what makes this a hard problem. NP complete. Yes. Sure. I mean, yeah. I mean, integer linear programming. I have this, and then I might also want to, maximize C transpose X. That goes along with an integer linear program. I didn't even bother writing it down because all I needed to do was find any solution, any feasible solution, and that would solve. That's a good enough to solve my 0-1 equations. Okay. All right. So we did 0-1 equations. We did integer linear programming. It's finally time to do graph theory again. So what I want to do is reduce this to Rajada Hamiltonian cycle, but it turns out we need a sort of a technical intermediate problem to get there, which is going to be, just add I need a gadget to make it work. So this is going to go from, so the intermediate problem that we're going to go to first is Rajada Hamiltonian cycle with paired edges, which I'll explain in a moment. And so I'm going to call this a shorthand WPE with paired edges. Okay, so that's going to be my intermediate step. So what is this problem? So I'm given a graph, the usual input for Hamiltonian cycle, and a set of edge pairs. Okay, so some finite list of pairs. And what I want to do is find a cycle that visits each vertex once. So far that's the usual definition of the Hamiltonian cycle. And here's the extra constraint. And it uses either EI or EI prime for all pairs in my list. Okay, so I have to use either one or the other. So let me do a little example to explain how this works. So here's going to be my graph. Okay, so 4 vertices and lots of edges. And it's easy to see, there are multiple solutions to this problem. But I'm going to restrict it, and I got to give these edges some names, so I can write this down. Okay, so those are the numbers of all the edges, and here is my set C. That means I have to use either E1 or E3, either E5 or E6, either E4 or E5. So you can see, you can have multiple appearances of the same edge in multiple of these pairs. E3 and E7, and E3 and E8. Okay, so that means I have to use exactly one from each of these 5 pairs. So one obvious cycle would be just to go around the outside, but you can convince yourself that that doesn't work. Let me tell you what the answer is to this particular problem. I will go from here to there, to there, to there, to there. That's going to be my answer to this problem. And so let's see if I've satisfied my constraints. So I've used E3. I've used E4. I've used E2. That doesn't appear. No big deal. I've used E6. Oh, there's E3. And I've used E6. But I haven't used 5, 1, 5, 7, or 8. So that satisfies the problem. Okay. And that's the unique cycle that visits everybody and uses exactly one of those. Okay. So let me show you how to build a graph with this constraint that captures the problem of 0, 1 equations. So write down a very small set of equations and then build a graph that corresponds to it. So here, let's see if I'm going to use all these colors again. Okay, so here is my matrix. It's going to be really small. It's going to have 3 rows and 1 column. And just to make it a little easier to see what's going on, so there's the first column. Here's the second column. Here's the third column. And here's the fourth column. Okay, and I want to multiply that by x1, x2, x3, x4, and I want that to equal 1, 1, 1. So that's going to be my system of equations. So what I want to do is build my decision about whether each of these is 1 or 0 into finding a path. And so here's going to be the trick. So on this side, I'm going to enforce a choice so there's just going to be a loop to go around this. And so I have to go all the way down here and all the way up here. And on each one of these, I have to decide left or right. That's going to correspond to is my variable 0 or 1. So I'm going to use this particular choice to distinguish between x1 equals 0 or 1. This choice to distinguish x2 equals 0 or 1. And I think I need 4 variables here. Excuse me. Give myself some more room. And then I need x3 and then x4. So depending on whether I go left or right as I go down this path, I'll decide on the value of x. So now this side is going to correspond to each of the equations and whether I've satisfied it or not. And so for the first equation, in order to satisfy this, I have to pick either the blue one, I either have to pick column 1 or column 3. I can't pick them both, right? Because I want these, I want these numbers here to add up to 1. So I have to pick either that one or that one. And so again, I'm going to have a choice. How do I pick either that one or that one? I'll either pick x1 equals 1, or I will pick x3 equals 1. That's the only way to satisfy the first one. And so here's my choice. I'll pick either x1 equals 1 or x3 equals 1. And that'll satisfy the first equation. And so how do I make my choices on either side consistent? I'll show you that. It's going to be picking the right set C. This is going to make sure I make consistent choices on the left and the right. Now, how about the second equation? I can either pick x2 equals 1 or x3 equals 1. So let me draw that. Or I can pick x3 equals 1. And the last equation, I have 3 choices. So I'm actually going to have 3 different paths to choose from. I can either pick x1 equals 1, or I can pick x3 equals 1, or I can pick x4 equals 1. Okay, so I want a cycle. It's obviously going to go around this whole loop, and the cycle is going to have to choose whether each variable is 0 or 1 and how I satisfy each of my equations. And so what I need to do is make sure I make consistent choices in the left and the right. And so this is how I'm going to do that. Let's see if this is going to fit. So what I want are consistent choices on the left and the right. And so here's how I'm going to pick my set C of pairs. So for example, if I pick x1 equals 1 over here, I can't pick x1 equals 0 over here. So I have to pick either that one or that one. So that's going to be how I make that consistent. So this is going to be either x1 equals 1 in equation 1, or x1 equals 0. That means I can either pick that one, because this corresponds to equation 1, or I can pick that one. I can't pick both of them, but I have to pick at least one of them. So what's the next thing that I need to decide on? X1 equals 1 in equation 3. It also appears here, right? So let me do that here. So x1 equals 1 in equation 3, or x1 equals 0. So if I pick x1 equals 0, I can't pick either of those edges. But I could pick either of those, and not that one. Okay, so let me just keep going. So how about x2 equals 1, and which means that I can either pick to go down that edge or down that one. I can't pick, both of those. So let me distinguish that one. So x2 equals 1 in equation 3, or x2 equals 0 over on this side. I can pick one. I have to pick one, but not the other. So I'm just going to walk down through every one of these appearances of a variable over here, and then match it to the thing that it can't do on that side. Okay, and then if I can find a path all the way around here, a cycle that satisfies all these, then I've satisfied my Rajata Hamiltonian path with paired edges problem. Okay. Again, a complicated gadget, but it's going to get us, we've gotten halfway to the real problem, which is, Hamiltonian cycle. Yes? Excuse me? Well, that's because in equation 3, I can either pick that one or that one. So let's see. No, this is x2, sorry. Yeah, so I can either pick x2 equals 1, or I can pick x1 equals 1. Sorry, let me get this right here. Yeah, this is equation 3, sorry. So I can either pick x2 equals 1, or I can pick x1 equals 1, or I can pick x4 equals 1. I have to pick exactly one of those. Yeah, I didn't finish writing in all of them, so yeah. Yes?
Doesn't the x2 appear in equation 2?
Let's see here. x2 appears in equation 2, yes. My bad. That should be equation 2. So, yes. So this is all about equation 2. Thank you. Any other typos or questions? Okay, so and the last thing is going to be Hamiltonian cycle. Which is, is there a cycle that visits every vertex exactly once? So the question is, how do I embed that problem into this pairs problem? So I need to another gadget that encodes this list of pairs that I can make up, an arbitrary list. Okay, so now I'm going to do this one, reducing that. And so what I need is another gadget to enforce the list of pairs. Okay, so let me just show you how that gadget works. So suppose one of those, so here's one of those pairs of edges, and let me just give them some names. So E is the edge from vertex A to vertex B, and E prime is the edge from C to D. Okay. So that means I have these two edges, A to B and C to D, and I'm only allowed to choose one of them. So how do I enforce that? So here's the trick. I want to add some cleverly chosen edges in the middle so that if you start there, you have to end there. And if you start there, you have to end there. So here's what it's going to look like. So I've just added lots of extra vertices and edges. So let's suppose, and there's no other way to get to these vertices other than, coming in and exiting through the ends. Yes? A, B, this should be a C, thank you. Yes. So I'm going to start at either A or C, and I have to come out at either B or D. So let's suppose that I start at A. So I come over here, and if I kept going, I would never be able to touch that one. So I have to go down. And if I went that way, then I couldn't get these guys in the middle, so I'm going to have to go that way. And then I have to go up, because otherwise I would miss that one. Then I would go over, same thing, and I have to come out at B in order to touch everything in the middle. There's no other way to do it. And similarly, if I started at C and I came in, I'd have no choice other than to take that path to get out. And so if I started A, I ended B, and if I started C, I ended D. And so I've sort of encoded my enforcement of choosing one of these edges by doing that. So that is the very simple trick. So so what if AB appears more than once? Okay. So what I'm going to do then is I'm going to introduce a new vertex right there, A prime, and do the same trick here. So I will, take this whole construction and say that I can either go from, so in other words, if I have another, let's say C prime D prime, then I'm going to change this to C prime D prime and build this whole construction right in there again. So again, I'll have a choice of either going that way or going that way. And if I pick that one, that satisfies both, or I can pick that one and that one. So that's sort of how the construction works. Okay. So I'm almost done. Any questions? So what I want to, so that means that I have not just, I have to choose one of A, B, and C, D. I have to choose one of A, B, and so C prime, D prime. And so what I'm going to do is change my constraint to A prime, and C prime, D prime, where A prime is this new vertex that I introduced. And so that means I either can choose that one or that one. And of course, if I choose that one, that means I do the blue one too. Yes?
Could we just have two vertical lines instead of four?
No, this is the smallest it gets. You can try it, drawing it, but yeah, this is the smallest it gets. Because we want to make sure we end up on the opposite side here, and that you can't loop back, and go out at C. That if you start there, you have to end there. Okay, so in my very last example is going to be taking this problem, redraw the Hamiltonian path, and reducing that to the traveling salesperson problem. So, and this one is going to be, so this is going to be on a graph with vertices and edges. And this is a graph which is going to have vertices and edges and weights. Okay. So, and what I want to do here is find the shortest path. Okay. So what I'm going to do is the following. I'm going to introduce some new edges and some new weights. So it's going to be the same vertices. So what is E prime? Equals E, all with weights 1. And I'm also going to add all other possible edges, all edges not in E, and the weight is going to be 2, or some number bigger than 1, doesn't matter. So it's going to be a complete graph. Everybody's going to be connected to everybody. The original edges will all have weight 1, and the new edges will all have weight 2. So now I'll solve TSP, the traveling salesperson problem, with this new one. If the total weight of all the edges is n, that means I only use the original edges. Because they all add up to 1. But if the total weight is greater than n, then there's no solution. Right? I had to use one of the new edges that I introduced in order to solve the problem. So that's how I distinguish it. It's a pretty simple reduction. Okay, so and we have 4 minutes for questions. Yes, go ahead.
Why did we even need e-prime in the first place if we already like set the weights to 1? Why do we need to set the weights for all that is not because
Yeah.
isn't e already like
No, well, this, I mean, this is an interesting problem because it's, we don't have all the edges, right? And so this is a subset of all possible edges. E prime has n, n squared edges in it, all pairs, n choose 2 edges in it. And I'm only distinguishing the edges by the original ones had weight 1 and the new ones have weight 2. In order to distinguish between whether I can find the shortest path only uses the original edges, and then I'm adding up, 1 plus 1 plus 1 n times, or I have to use one of those new edges to solve the problem, in which case it's bigger. So that's the distinction. Yes?
So on that board right behind you, where did A prime come from?
I just invented it. I stuck it right there. I just gave it a name. I mean, I had to invent it in the first place, right? These are all brand new vertices I added to my graph, and I'm just giving that one a name, A prime.
So it represents the original A, right?
Yeah, right. It just sort of represents the original A. Okay, so next time we will talk about practical algorithms to solve all these problems.